Hi, everyone. Welcome to the analysis seminar. We're happy today to have Blake Keeler from McGill University, who's going to tell us about the two-point Weyl Law on manifolds without conjugate points.
Thank you very much. I'm happy to be here. So to get started, I'll introduce just a little bit of notation. We're going to be working in the setting of MG, which is a smooth, compact Riemannian manifold without boundary. I'll denote its dimension by little n, which will always be at least 2. I will let delta G be the Laplace-Beltrami operator on M, taken with the sign convention that it's a non-negative operator. So there's an implicit minus sign in the definition. And because of the compactness of M, we know that we get an orthonormal basis of eigenfunctions phi j with the property that the Laplacian acting on phi j gives us back lambda j squared, the eigenvalue, times phi j. And they're normalized so that their L2 norm is 1. And we can order these lambda j in increasing order tending to infinity, and we'll repeat them according to their multiplicities. Eigenfunctions are intrinsically interesting in and of themselves, but they also have a deep connection to quantum mechanics. In particular, if you take the modulus of phi j squared times the Riemannian volume form, this gives you the probability density of a quantum particle with energy lambda j squared. So the main question I'm going to be interested in today is how do these lambda j and phi j behave as j tends to infinity? So we're looking at the high frequency limit, or if you prefer to rescale things, this is equivalent to the semi-classical limit as h tends to 0. To this end, I'll introduce a couple of primary objects of interest, the first being the eigenvalue counting function, n of lambda, which is just the number of lambda j that are less than or equal to lambda. More generally, I'll also talk about the spectral function, which I'll denote by pi lambda, and it's a function of points x and y on the manifold, defined as the sum over all lambda j less than or equal to lambda of these pointwise products of eigenfunctions, phi j at x times phi j at y. And this is a spectral projection from L2 onto the eigenspaces with eigenvalue less than lambda squared. And ordinarily, you'd have a complex conjugate here, but without loss of generality, I can take the phi j to be real valued, so I don't need it. Now, this pi lambda is actually more general in that it contains strictly more information than the counting function, because we can recover n of lambda from the trace of pi lambda. So if I compute the trace, which is just the integral of the restriction to the diagonal, I can use the orthonormality of the eigenfunctions to rewrite this as a sum of just a bunch of ones. And so we recover exactly n of lambda by computing the trace of pi lambda. So we'll focus our study mainly on pi lambda here. And as a point of terminology, the asymptotics of both n of lambda and pi lambda as lambda tends to infinity are broadly referred to as Weyl laws. And these have a long history dating back to the early 1900s with the work of Weyl for bounded domains in Rn. Unfortunately, we don't have time for a full history lesson, and so I'm just going to cut straight to the case of manifolds, which was done in the 1950s. This is due to Avramovich building on earlier partial results of Levitin, who showed that on any manifold Mg, we have the following asymptotic for the counting function n of lambda. It looks like a constant times lambda to the dimension as its leading term, plus a remainder, which is one polynomial power better in lambda, as lambda tends to infinity. And they also showed an asymptotic for the on-diagonal spectral function, so pi lambda restricted to xx. We get a different constant times, again, lambda to the n, plus the same size remainder. This can be seen to be sharp if you consider the case of the round sphere, where the symmetry of the sphere leads to very large multiplicities of your eigenfunction, or excuse me, eigenvalues, which in turn gives you the sort of maximal remainder growth. So you can't do better than lambda to the n minus 1 without imposing some additional restrictions. The results were generalized significantly by Hormander in the 1960s, who showed that on any manifold, there exists an epsilon positive, such that if the distance between x and y is less than epsilon, we can write an asymptotic for the two-point spectral function, pi lambda of x, y. And it's going to look like, once again, lambda to the n with a more complicated leading coefficient here that's now a function of lambda x and y. And I can write this down explicitly in a moment, plus a remainder, r of lambda x, y, which satisfies the following bound. You can take the supremum over all x and y, which are less than epsilon apart, of the remainder, and it is, once again, O of lambda to the n minus 1. Now, I've left some weird spaces in here very intentionally, because you can actually improve this in the sense that you can differentiate with respect to x and y, and it modifies the remainder in a very predictable way. So this was done by Xu in 2004, who showed that if you take covariant derivatives in x and y, of orders alpha and beta, then this corresponds to an increase in the bound for the remainder by exactly the order of differentiation. And we can write down this leading order term explicitly. It's a little bit ugly, but it's not too terrible. It's a constant times this integral over the unit ball in the cotangent space of this oscillatory exponential that whose frequency depends on lambda times the standard volume form on the cotangent space. And so you can see that when you differentiate this leading order term with respect to x and y, you will have powers of lambda spit out according to the order of differentiation. And so this remains the leading order term even when you differentiate, despite the fact that the remainder is now getting larger and larger as you differentiate in x and y. And once again, this is sharp, as can be seen in the case of the round sphere. In fact, it follows from the fact that the on diagonal is sharp because you can just restrict to x equals y.
Excuse me, Blake, can I ask a question? I have a hard time having a feeling for what the derivative of the remainder measure. Like the remainder tells me something, but what about its derivatives?
Derivatives of
the
this
remainder
leading term? Of the remainder.
Yeah, does it measure something intuitively? What does it tell me that we know that when you differentiate it, it is still bounded?
So it's useful in the study of monochromatic random waves, which I will discuss in a little while. It turns out that when you have bounds on the derivatives in x and y, you can show that monochromatic random waves exhibit some universal scaling behavior that's independent of the manifold, and that you get that scaling behavior, you get a convergence in the C infinity topology when you have this derivative out here.
Okay, thank you.
I also have a question. So in this formula, if x is different than y, then if you're off diagonal, then I assume your coefficient Cm has to vanish, right?
If the distance between x and y is bounded below, then yes, you're going to
have.
No,
but if you're just if you're just at two different points, then if you're off the diagonal, then you should not have a term with lambda to the power n.
If you fix x and y as lambda tends to infinity, you're correct that this oscillatory term will have some decay in lambda. Generally, what's done is to study, the interesting stuff happens when you take the supremum over a shrinking neighborhood of that diagonal. If you looked at, say, distance between x and y being less than 1 over lambda, and then the size of that neighborhood of the diagonal competes with the growth of lambda here, and then you have a meaningful asymptotic.
Sure. So I just missed the depend. Yeah. Okay. So now everything makes sense. Thanks.
Okay. I'm primarily interested in cases where we can improve this remainder, but since these are all sharp, we know that we're going to have to introduce some kind of geometric restrictions on our manifold in order to make any improvements. And it turns out that the correct object to make assumptions about is the geodesic flow. There's an intimate connection between the asymptotics of pi lambda and the structure of the geodesic flow on the underlying manifold. And this can be seen in a fairly straightforward manner. So if I write down the definition of the spectral function, I can rewrite this sum over lambda j less than lambda as a sum over all j, where I've artificially introduced this characteristic function of the interval minus lambda lambda. Using the symmetric interval just introduces some convenience for me. And then using the Fourier inversion formula, I can rewrite this characteristic function as the inverse Fourier transform of its Fourier transform, which leaves me with an expression of the following form. I get an integral over t, this sine t lambda over t, which comes from the Fourier transform of the characteristic function. And because I use the even characteristic function, I get a cosine t lambda j instead of an exponential. And so we can immediately recognize this sum over all j as the spectral representation of the cosine propagator. This is just the cosine of t square root Laplacian. I can write the spectral function as the inverse Fourier sine transform of the function 1 over t cosine t square root Laplacian. And we know the general fact about the Fourier transform in that it intertwines growth and decay at infinity with singularities and smoothness. So if you have some finite order singularity, then the Fourier transform will have some polynomial degree of growth at infinity, which corresponds in some way to how bad the singularity was. By finite speed of propagation for the wave equation, we know that the cosine propagator has its singularities propagating along geodesic spheres. And so it's natural to expect that the growth of pi lambda as lambda tends to infinity should be in some way related to the geodesic flow on the manifold, because the geodesic flow carries the singularities of the cosine propagator. And indeed, this is the case. This is not just a heuristic. If you look at a result of Duistermaat and Gilliman from 1975, they show that if you assume that the set of periodic geodesics on your manifold has measure 0 with respect to the Liouville measure, then you can improve the Weyl law by a little bit. So you have the same leading order term, but then there is a little o of lambda to the n minus 1 instead of a big O. So there's a non-quantitative improvement, but an improvement nonetheless. This was generalized to the on-diagonal spectral function by Safarov in 88 and later independently by Sog-Zeldich in 2002, under the slightly stronger assumption that if the set of geodesic loops starting at some point x0 in M has measure 0, then the spectral function at x0, x0 has a little o remainder bound instead of a big O. So the set of geodesic loops having measure 0 is slightly stronger because it excludes the case where you have a geodesic which returns but has a different velocity. So it's not periodic, but it's still looping. And so you have to exclude those as well. And this was further generalized to the off-diagonal case by Kanzani and Hanin, who showed that, again, under this geodesic loop assumption, you can pick a radius r lambda, which shrinks as lambda tends to infinity. Then for any x and y in the ball of radius r lambda centered at x0, we have the standard asymptotic for the off-diagonal spectral function, but where now the remainder, if you take the supremum over this ball, satisfies a little o bound instead of a big O bound. So again, we've improved the sharp bound by just a tiny little bit by excluding these periodic geodesics, or geodesic loops rather. Now, what I'm interested in is when we can get quantitative improvements in the remainder. I want an explicit function that tells me how much better my remainder is than the general case. But in order to accomplish that, we need an even stronger geometric assumption to make that work. And one result that's of particular interest for my talk is that of Berard from 77, who showed that if you have a manifold with non-positive curvature, which implicitly is an assumption about the geodesic flow, because it means that all of your geodesics are going to be spreading apart at least linearly, then you can improve the remainder in the Weyl law for the counting function by a factor of 1 over log lambda. So we're back to a big O, but we have a quantitative improvement in the rate of growth of the remainder. And moreover, he showed the same thing for the on-diagonal spectral function, and we retain the log lambda improvement. Now, Berard didn't explicitly state this result in his paper, but his proof shows this with no modification. Now, in the case of dimension 2, Berard was able to show this under the weaker assumption that the manifold has no conjugate points. But there were certain geometric estimates that he was unable to obtain in higher dimensions without the non-positive curvature assumption. This was remedied, however, fairly recently by Bontenot in 2017, who showed that these geometric estimates that Berard needed still held in higher dimensions under the no conjugate points assumption. And so the rest of Berard's proof goes through in the weaker case of no conjugate points. With this context, I'm ready to present the first result of the talk, which you may be able to guess what it's going to look like because there's a bullet point suspiciously missing from this slide. Namely, I haven't shown you an off-diagonal version of this Weyl law for no conjugate points, which is exactly the content of theorem 1. So if we suppose that mg has no conjugate points, and we fix some epsilon between 0 and half the injectivity radius, then we can write down the Weyl law for the spectral function at xy, and its remainder satisfies what you might anticipate. Namely, we get the same power of growth as in the sharp case, but it's improved by a factor of 1 over log lambda. And we can take the supremum over a fixed neighborhood of the diagonal of width epsilon. Now, you might ask, well, as Joseph already did, what happens when you're away from the diagonal? If you have some kind of, if your distance between x and y is sort of bounded below, you should have negligible contributions from this leading order term. And indeed, that is the case. You can show, which is the content of theorem 2, that if you fix an epsilon positive and you take the supremum over all x and y, which are bounded away from each other by a distance epsilon, and you estimate the spectral function itself, not the remainder, then this will have the same upper bound that the remainder did in the two-point Weyl law on theorem 1. So if you are bounded away from the diagonal, then the spectral function is sort of negligible if what you care about is the lambda to the n behavior.
Like, do you have control over the behavior in epsilon here of the O, of the big O?
There is, I don't think so that you can't choose epsilon in a way that depends on lambda in a way that's too bad. Like you can choose epsilon to shrink in a way that depends on lambda, and you can work out exactly what it is. It's like log lambda to the 2 over n divided by lambda. Like there's some region around the diagonal which is slightly bigger than the 1 over lambda window that you can still maintain the leading order term from theorem 1.
Okay.
I don't recall exactly what it is, but you can push epsilon down to something that shrinks with lambda as long as it doesn't shrink too fast. This result about the supremum over the spectral function, where you take the supremum over x and y bounded apart, is similar to a result of Safarov, who showed that if you have a compact set K in M cross M, which avoids the diagonal and satisfies some technical dynamical assumptions, then you can take the supremum over this set K of the spectral function, and you'll get a little o of lambda to the n minus 1. So it can be sort of lumped into the remainder term from the Weyl law.
And Blake, in non-positive curvature, you don't have conjugate points, but you have cut points, right? So where maybe several geodesics come together. So you choose, fundamental domain and another point on the boundary of fundamental domain. Is there anything special in that case? It's kind of an idle question. I don't know.
I don't have an answer to that immediately. We can talk more after potentially, but I haven't really thought about that.
But this is like non-positive curvature analog of conjugate points in some sense, right? So things should be somewhat special for points that are cut points, but it's also a geometric condition. Of course, it should be much smaller than conjugate, but the conjectures are fairly strong, right? Infinity conjecture. So anyway, thanks. Sorry.
We can talk more after potentially.
Sure, of course.
So the final main result I want to talk about requires a little bit more notation, namely that of a spectral cluster. So I'll define a spectral cluster by the following. So I'll write pi with a subscript of an interval, and it's going to be defined as the sum over lambda j in this window of these pointwise products of eigenfunctions. So it's the projection from L2 onto this window of eigenvalues. We can prove an asymptotic for these spectral clusters as well in the case of no conjugate points. So if you suppose MG has no conjugate points and fix an epsilon as before, then these spectral clusters satisfy an asymptotic where the leading term is like lambda to the n minus 1 times a similar leading order term as before, but it's now an integral over the unit sphere rather than the unit ball. And we integrate with respect to the spherical measure instead of the volume measure.
And what is ins mg?
This is the injectivity radius of the manifold. It's the smallest. It's the smallest radius of your normal coordinate neighborhoods. So, basically, if the distance between x and y is smaller than epsilon, then you have a nicely defined diffeomorphism given by the exponential map. So, and also the remainder here satisfies the same upper bound as it did in theorem 1, where now the difference between the leading order term and the remainder term is a little bit smaller. In fact, it's only this log lambda that makes this a meaningful asymptotic, because the leading term here is lambda to the n minus 1, and the power on the remainder is like lambda to the n minus 1 plus the order of differentiation. So the fact that I have a quantitative improvement here is really all that makes this a meaningful asymptotic as lambda tends to infinity. Otherwise, the remainder and this term, which I claim is the leading term, would be competing with each other. Theorem 3 has a particular application to the study of monochromatic random waves, which I will define now. I will set a monochromatic random wave psi lambda of x to be this sum over lambda j in this window from lambda to lambda plus 1 of these coefficients aj times phi j, where I've rescaled by lambda to the 1 minus n over 2, which corresponds roughly to rescaling by the square root of the number of eigenvalues in this window. The kicker here is that the aj are not deterministic coefficients. They are instead independent, identically distributed Gaussian random variables with mean 0 and variance 1. So we can think of this as a sort of randomized approximate eigenfunction, or quasi-mode, if you like. The study of these random waves on manifolds was introduced first by Zeldich, who was motivated by Berry's conjecture, which I don't want to talk about in too much detail. It's somewhat vague and heuristic, but the idea is that if your manifold has chaotic geodesic flow, then your eigenfunctions at high energy should have some kind of universal scaling behavior to them. They should behave roughly like a certain Bessel function on Rn. The Gaussian random waves that we're looking at, these monochromatic random waves, are a way of approaching Berry's conjecture with a little bit more wiggle room, where you study these randomized quasimodes instead of true eigenfunctions. And the benefit that we get from doing that is that we can completely characterize the statistics of psi lambda by the corresponding covariance kernel, or two-point correlation function, which measures the covariance between psi lambda at x and psi lambda at y. So we're looking at how the values at x and at y are correlated with one another. And you can compute this explicitly, and all of the statistical quantities get integrated out, and you end up with something that looks very familiar, namely exactly the spectral cluster that I defined previously times a factor of lambda to the 1 minus n. So theorem 3 has an immediate implication for the covariance kernel of these monochromatic random waves. So on a manifold with no conjugate points, if we fix some point x naught and we choose a radius which can grow at most like square root lambda over log lambda, we can write a limit, or excuse me, something that's better than an asymptotic. We can write an actual convergence statement for the covariance kernel in geodesic normal coordinates centered at x naught. So I look at the covariance of psi lambda at x naught plus u over lambda, x naught plus v over lambda. So u and v are my normal coordinates in Rn, and I've rescaled them by 1 over lambda. And this covariance kernel equals an object I'll call pi infinity, which does not depend on lambda, and I'll write it down in a second, plus a remainder, which tends to 0. So I could take the supremum of this remainder over all u and v, which are smaller than this radius r lambda, which I will note does grow as lambda tends to infinity. All of the derivatives of this remainder tend to 0 like 1 over log lambda. So this is a convergence result in the C infinity topology for the covariance kernel of a random wave. And as I mentioned, this pi infinity can be written down, and it's just the inverse Fourier transform of the spherical measure, which in turn can be written in terms of the Bessel function of order n minus 2 over 2. Have a universal scaling limit for monochromatic random waves in the case where your manifold has no conjugate points. Now, mind you, this is not by any means a proof of Berry's conjecture, since I've only shown this for monochromatic random waves, not for true eigenfunctions, but it is a step in the right direction. So with that, I will move on to the proof of theorem 1, unless there are any questions. Well, then I will start with a brief outline of the steps of the proof. Step 1 is to sort of regularize the spectral function as a function of lambda. So it has jump discontinuities at each of the eigenvalues, lambda j. And so what we will do is convolve with a certain Schwartz function to smooth out this dependence on lambda in a way that doesn't affect the asymptotics at infinity. And what we'll see is that this is equivalent to restricting the support of the cosine kernel as a function of t. And the larger the size of the support we can allow, the better of a remainder estimate we will obtain. Once we have smoothed the spectral function and restricted the support of the cosine kernel, our goal will be to approximate the cosine kernel with a parametrics for logarithmic timescales. So we'll use the Hadamard parametrics to approximate the true cosine kernel with something that we can explicitly compute. And then the third step will be to compute the explicit asymptotics using each of those individual terms from the parametrics. And then the final step, which is my favorite, is you just throw everything in a giant triangle inequality and you call it a day. So we can estimate the difference between pi lambda and the thing I claim is the leading order term. And this can be split up as the contributions from steps 1, 2, and 3. And all of these we will show is bounded by the remainder estimate that I claim in theorem 1. So with that, let's get started with step 1. I'll introduce a Schwartz function, which I'll call rho a, which will be a function on R, with the property that its Fourier transform is smooth and compactly supported. It's even, and it's supported in a window of size 1 over a, where a is a parameter between 0 and 1. So as a gets closer to 0, it corresponds to a larger and larger support of this cutoff function. And then I'll convolve my spectral function with rho a, where the convolution is taken in the lambda variable. And by properties of the Fourier transform, this corresponds to simply multiplying by rho a hat in that Fourier expression that we had for pi lambda. So what we're doing here is restricting the support of the cosine kernel to this interval -1/a to 1/a. So as a tends to 0, this corresponds to a larger and larger time scale on which we must control the cosine propagator. Now we have to control also the error between the true spectral function and this new smoothed out version. We have to show that regularizing in lambda does not affect the asymptotics as lambda tends to infinity. And for that, we need a proposition. So on a manifold without conjugate points, we can pick any parameter a between 0 and 1. And then I claim that we can estimate spectral clusters of width a in a particular way. So I'm taking the supremum over x. I take the spectral cluster from lambda to lambda plus a. I'm differentiating in x and y the same number of times in both variables and restricting to the diagonal. So this is an on-diagonal spectral cluster estimate. And I claim that the upper bound here depends on a in the following way. I get a lambda to the 2 alpha from the derivatives. And then the leading term here is a times lambda to the n-1 plus an exponential in 1/a times some powers of lambda that are significantly smaller. So the key here is this exponential dependence on 1/a. It is this that leads us to the choice of a to be 1 over a constant times log lambda, because if we choose a to be of this form, then this exponential term will turn into a lambda to the epsilon for some small epsilon, as long as we choose our little c small enough. And the proof of this proposition, I'm not going to go into right now because it involves a repetition of many of the arguments from steps 2 and 3 of the main proof. So we'll be using a parametrics and doing explicit asymptotic analysis, just with it just involves a choice of a slightly different cutoff function. So I won't discuss the proof of this proposition here.
But this exponential estimate is a bit like in the proof of Berar. It comes from dynamics and Lyapunov exponents and so on, or?
Yeah, it arises because of the geometric estimates that you can get on the universal cover, because you can only get at best, or at least without changing your techniques, you can at best get exponential estimates in T on the difference between the true wave kernel and the parametrics.
Okay. And but if you had, like, let's say integrable flow, then this would be better.
Yes, I would expect that you would get better estimates on the error in your parametric expression if you had better control on the geometry of the universal cover.
Okay, thanks.
And I believe this manifests in the case of the flat torus. I think you can see that show up in the proof, and you get a polynomial dependence here. So using this spectral cluster estimate, we're able to bootstrap our way up to estimate the difference between pi lambda and the smoothed out spectral function. So we can estimate the difference by what I claim the remainder in theorem 1 is, this lambda to the n-1 plus alpha plus beta over log lambda for the appropriate choice of a. And the way we prove this proposition is essentially writing the sum over all lambda j as a sum. If we break the sum up into windows of width a, on each window of width a, we apply this proposition. And then we show that each of those estimates can be summed in j, and we end up with the desired estimate because of this factor of a that shows up in the first proposition. So when we choose a to look like 1 over log lambda, we get the desired behavior in this estimate. Now that we know that we can smooth the spectral function without ruining the leading order term, we can move on to approximating the wave kernel with the Hadamard parametrics. So the Hadamard parametrics is a construction that works on any manifold. And this theorem is that there exists coefficient functions u nu, which are smooth, and some distributions w nu, such that for t less than the injectivity radius of the manifold, we can write the cosine kernel as an expansion of u nu times w nu, and w nu are evaluated at the distance between x and y because there's spherical symmetry in the cosine kernel. And this equality holds mod c infinity at the level of Schwartz kernels. I won't go into too much detail about what the particular form of these u nu and w nu is, but roughly speaking, the u nu encode the geometry of your manifold along the geodesic which connects x and y. And the w nu are homogeneous distributions which encode the singular structure of the wave kernel. In particular, w0 is up to a change of coordinates, just the fundamental solution or the cosine propagator in Euclidean space. And you can write that down very explicitly. And as nu increases, the w nu will get more and more smooth. The problem here is that this is only valid for t less than the injectivity radius. And this is not good enough for our purposes because we want to control the wave kernel intervals where t is going to look ultimately like log lambda. So we need to control the wave kernel for much, much longer timescales than this theorem allows. And it's here that we use the no conjugate points assumption to understand the long time behavior of the wave kernel. Use the no conjugate points assumption to lift to the universal cover, which is simply the cotangent space at some fixed base point, whichever one you like, equipped with the pullback metric, where P is the covering map. And I'll denote the universal cover by M tilde with the metric G tilde. So everything that has a tilde on it will live on the universal cover. Now I can apply the theorem of Hadamard to build the Hadamard parametrics on the universal cover, which gives me the same expression as before, just with tildes everywhere. And this is now valid for all T in R, because the injectivity radius of the universal cover is infinite. Now I'll induce a parametrics on the base manifold by summing over the deck transformation group. So your capital gamma is the deck transformation group, and I sum over all translates of Y tilde, where Y tilde is some lift of Y. Because I've summed over all of the deck transformations, I get an object which is invariant under the action of the deck transformation group, and so it induces a uniquely defined distribution on the base manifold. And this expression is still valid for all T in R. It's worth noting that although the sum over gamma in theory is infinite, it's really not, because all the terms except finitely many will be zero because of finite speed of propagation of the wave equation. So these W nu have support in the light cone. And we can actually estimate the number of terms that appear, and the estimate is exponential in T, which is good for us because we're choosing T to look like log lambda. And this estimate on the number of terms is due to Coulomb de Verdier. So we have now produced a parametrics on the base manifold, which is valid for all time. However, in the process, we have lost the compactness because M tilde is not compact, it's diffeomorphic to Rn. And so now geometric quantities as functions of X and Y, which would have been bounded by default, now need not be. And so we're going to need some bounds on, in particular, these coefficient functions and the distance function, and also the exponential map. So what we need is exponential control on the derivatives of the Hadamard coefficients, the Riemannian squared distance, and the inverse exponential map. So that's the goal of the next proposition. So if we have the universal cover of a manifold without conjugate points, then all of the Hadamard coefficients and all of their derivatives are bounded exponentially in the distance between X and Y. And similarly, the derivatives of the squared distance function and of the exponential map, excuse me, the inverse exponential map, are also bounded exponentially in the distance between X and Y.
Shouldn't this exponential bound be always true? I mean, just by, you really need to assume that you have no conjugate points for an exponential bound?
I believe so, yes. So I am not aware of a method of proving that the exponential bound always holds. In fact, these are the estimates, or well, particularly this one, are the estimates that Berard needed to get his result in the case of non-positive curvature that he was unable to get in the case of no conjugate points for dimensions higher than 2. So Bontenot's contribution was to prove these estimates in the case of no conjugate points where you restricted to, without the derivatives in X and Y here. So you can estimate all of the Hadamard coefficients exponentially in the distance. And my contribution here is to show that you can differentiate them, and as well as the distance function and the inverse exponential map, and these exponential bounds remain true. And it relies heavily on the fact that there are no conjugate points. I don't know if you can prove a negative, like the opposite direction, where if you don't have no conjugate points, then you can somehow find a counterexample. I'm not aware of any counterexamples, but the proof of Bontenot and the proof in my paper both heavily rely on the no conjugate points assumption. Does that answer your question?
Yeah, I suppose.
So I won't go into too much detail about the proof. I'll just make a few small remarks. First is that the U-nu are defined recursively. And so it suffices to only estimate the derivatives of the first one, U-naught, which is defined as the geometric theta function to the -1/2, which is in turn defined as the determinant of the differential of the exponential map raised to the -1/2. And so in order to estimate this quantity, we can look at Jacobi field methods, because the derivatives of the exponential map are naturally related to Jacobi fields. And so we can estimate the derivatives of theta by analyzing a 2n-dimensional variation through geodesics using Jacobi field methods. This is a generalization of a technique used by Matt Blair to prove geodesic restriction bounds in the case of non-positive curvature. And the proof is heavily geometric, and so I'm not going to go into the details, But this is the general strategy, is to look at a variation through geodesics to rewrite the derivatives in terms of these vector fields, and then estimate those vector fields using the no conjugate points assumption. And a similar thing is done for the square distance function and the inverse exponential map, because they can all be expressed in terms of the exponential map itself. So once we know that the derivatives of these geometric quantities are not going to be a problem as the distance becomes large, we have this exponential control, we can move on to using partial sums of the Hadamard parametrics to replace the true wave current in our integral expression. So I'll define these partial sums to be k sub n, where I've just now truncated the sum over nu. So this is truly a finite sum. And I claim that the error involved in replacing the cosine kernel by one of these partial sums of the parametrics is bounded by t times an exponential in t. So it's exponential as t tends to infinity and vanishes as t goes to 0. This is true for all derivatives of the error as well. And we can take the supremum over all x and y in M. So this is a global estimate on the error involved in replacing the true cosine kernel by the parametrics. And this exponential bound in t is sufficient for our purposes because t is going to be restricted to be at most 1 over a, which in turn looks like a constant times log lambda. So these exponential bounds in t can be made to look like a lambda to the epsilon for some small epsilon, as long as we choose our little c sufficiently small. So we now know that we can replace the cosine kernel with the parametrics. And now the final main step of the proof is to compute the explicit asymptotics using these parametrics terms. And this is a lot of technical computations that I'm not going to show you. I mean, if you're interested, I can show you after, I suppose. But there's a lot of legwork that goes into this. So I'm only going to sketch the main results that you get from the different types of terms that appear. So the goal is to estimate quantities of this form. We have our integral over t. We have our cutoff function rho a hat times this sine t lambda over t that's been following us around. And then the terms of the parametrics, which depend on two parameters. They depend on nu and they depend on gamma. And so I'm going to split this into two cases. The first, where gamma is the identity transformation, and the other where it's not. And the fact that I can make a meaningful distinction between these two does rely on the fact that x and y are at least somewhat close to each other. So there's a unique closest pair of lifts, x tilde and y tilde. In the case where gamma is not the identity, things are a bit easier. So in this case, we can bound the distance between x tilde and the translate of y tilde below by a positive constant, which implies that the singularities of W nu, which occur at the boundaries of the light cone, so plus or minus the distance, these singularities are bounded away from each other. And so we can estimate the contributions of these singularities independently and just add them up. And what we get is something significantly smaller than the bounds claimed in remainder in theorem 1. In particular, is something like lambda to the n minus 1 over 2 with a small modification. So much, much smaller than the lambda to the n minus 1 over log. This step does involve heavily the geometric estimates from step 2, because we're looking at gamma not being the identity, so we're potentially translating y very, very far away from x. And so we need to be able to control the size of these quantities as the distance grows with lambda. The case that gives us the leading order behavior is when gamma is the identity. So when x tilde and y tilde are the unique closest lifts of x and y in the universal cover. Here, things are more subtle because the singularities can be quite close together, but not necessarily exactly coincide. If you were restricting to the diagonal, x equals y, then your expression for this integral in t would simplify a lot. It would reduce to basically just an inverse power of t, and computing the inverse Fourier transform of that is fairly straightforward. When x and y are not necessarily exactly equal, but still quite close, you have to track the dependence on the distance between x and y in a very careful way. When you do that for the most singular term in the parametrics, which is W0, you get exactly the leading order term that I claim, which follows from a sort of direct computation using the fact that W0 is essentially, up to a change of coordinates, the cosine propagator in Euclidean space. So you can compute this leading term very explicitly. And the remainder is indeed smaller than this lambda to the n minus 1 over log. The way that this appears is because of the factor a that will pop out from the fact that this size of our cutoff function support is of size 1 over a. And so there are factors of a that show up in the remainder that give us this 1 over log here. Once you've estimated W0, the rest of the terms are significantly smaller because as you increase nu, each W nu will become less and less singular, and therefore the contributions as lambda tends to infinity will be significantly smaller. In fact, it will look something like lambda to the n minus nu minus 1 plus the order of differentiation. So for nu greater than or equal to 1, this is at least lambda to the n minus 2. It's much smaller than the claimed remainder bound here. So that's all I'll say about the explicit asymptotic analysis. There's a whole lot of details that go into this, but this is the highlight of the results. Given this, we're now able to throw everything into a giant triangle inequality and complete the proof of theorem 1. Distance between x and y less than half the injectivity radius. We can estimate the difference between pi lambda of xy and the thing I claim is the leading order term. We split it up into the contributions from step 1, 2, and 3, which we'll recall step 1 was looking at the difference between pi lambda and rho A convolved with pi lambda. So this was smoothing the spectral function. Step 2 was replacing the cosine kernel with the parametrics. And step 3 was explicitly showing that that parametrics expression has the leading order term that we want, plus a remainder which satisfies the bound that we're looking for. And so the errors accumulated in all 3 of these steps are indeed smaller than lambda to the n minus 1 plus alpha plus beta divided by log, which completes the proof of theorem 1, modulo all of the details. So the proofs of theorems 2 and 3 are built off of essentially the same framework with a little bit of a change in perspective here and there. And so all of the meaningful information in the proofs is contained within the proof of theorem 1. With that, I'll talk briefly about some ongoing work. So an analog of the scaling limit result for monochromatic random waves, this corollary 1, is conjectured to hold on any manifold with at least little o of 1 convergence, provided that you choose your intervals to define your monochromatic random waves, I lambda, to have enough eigenvalues in them. So if there are at least big O of lambda to the n minus 1 eigenvalues in the interval, you expect to see the same scaling limit behavior for monochromatic random waves. This is a conjecture due to Zeldich, and in collaboration with Shizak Kansani and Jeff Galkowski, I'm investigating the behavior of the spectral function on Zoll manifolds, where all of your geodesics are periodic with the same period. So this is the opposite extreme of the case of no conjugate points. And we are able to show, although the paper is not completely written yet, that you get the same leading order behavior for your monochromatic random waves if you choose the intervals I lambda to be centered on the eigenvalue clusters. Because the Zoll manifolds have their eigenvalues strongly clustered near a predictable sequence of values. And so if you choose the I lambda to be centered on those intervals, you still have enough eigenvalues inside in order to get the leading order behavior that you want. Something else I'm interested in relation to this theorem 1 that I presented is whether it can be upgraded to a local statement. So if you only assume that a fixed point x0 in M has no conjugate points, can you still get the logarithmic improvement in a small ball centered at that x0? So the main thing here is that the geometric estimates from step 2 involve knowing that you have no conjugate points globally. The question I have is whether if you only assume that x0 has no conjugate points to it, can you find a small enough ball around x0 where everything in that ball also has no conjugate points? If that were true, then you could get all of the geometric estimates that you need and prove a local version of theorem 1. But I'm not sure if that is true. And if anyone has any ideas about that, please feel free to let me know. I'd love to talk about it with you. And with that, I will thank you for your attention. Thank you for the invitation to speak. And here are some references in case you'd like to do some further reading on the topic.
Right, let's thank Blake for his talk. Are there any questions or comments?
Blake, sometimes we can get lower bounds for the remainder, which are much worse, but still of some interest, right? I mean, I guess my question is kind of related to the question of Alexander. Can we get interesting lower bounds for derivatives? And can we maybe in some examples get interesting, like some interesting pairs of points where you would expect where some of these functions would be bigger than what's predicted by random wave conjecture. So for example, right, I mean, there are very special arithmetic manifolds where at certain points eigenfunctions in negative curvature can be polynomially large Hügner points, right? So get something for off diagonal spectral function. So something like that.
A very interesting question. I don't have an answer to that. I haven't looked into that too much. I've been looking at the papers of yours and Yosef's about those lower bounds on the spectral function, and I'm curious to see if anything can be done to get lower bounds for derivatives of the off diagonal remainder. But I don't have anything concrete in that direction at the moment.
But I guess, I mean, if you somehow understand something nice about what Alexander was asking, what's the geometric meaning of these derivatives, then maybe you could get some geometric intuition, like where to look. So.
No, it's a very good question. I unfortunately don't have any answers about lower bounds at the moment, because everything here is geared very much towards just estimating from above. But finding interesting points, interesting pairs of points, where you get sort of the worst behavior that are not necessarily on the diagonal would be a very interesting thing.
Like, maybe can I ask a silly question? Can any of this be done if you have negative curvature, but you have a boundary, the convex boundary or something?
Well, I can't say for sure that it doesn't, like that a similar result doesn't hold, but I don't know what the technique would look like, because the core of this is built off of lifting to the universal cover. And I'm not aware of a meaningful way to make sense of that if you have a boundary.
Right. So presumably, like at some points, like on the boundary, you'd have a Dirichlet boundary condition. So spectral kernel would just be 0. But then there's some also asymptotic as you approach the boundary. It goes from being lambda to the n to being 0. And so there's some rate at which it falls off.
Right.
I recall I think there's work of Sagan-Zeldich in the boundary case as well. I don't know exactly how general it is, but under convexity and concavity assumptions on the boundary, I don't know if it's a direct answer, but I think there's sort of boundary analogs of these little O estimates that are known.
Yeah, I mean, if that's the case, I mean, it could be interesting also to do this quantitative improvement, this log lambda stuff that Blake seems to be specialist at.
Yeah, I think it would require an overhaul of the techniques for sure, because I don't think this lift to the universal cover method would apply in that case.
I guess another silly question is what happens for the spectral function on a graph. Like for eigenvectors, people looked at a lot of things, but for a spectral function, maybe a little bit less. I mean, there are some conjectures how there is an analog of random wave for for constant degree, regular graphs. But
I think this is the same question that Dima was asking earlier. But so you don't know how sharp theorem 1 is?
No, I'm not aware of any way of knowing that the log lambda result is sharp, and in fact I would be very surprised if it was sharp. It's sort of, we do a whole lot of work to get a very small improvement in the remainder bound, and the no conjugate points assumption is a fairly strong geometric assumption. You have a lot of information about the geodesic flow, and I would be surprised if log lambda was all that was theoretically true, but I don't know of a way that you could prove a better bound without a serious revamping of the techniques. If you had better control on the geometry of the universal cover, and you could get estimates that were better than exponential in the distance between x and y, if you could get some kind of polynomial control on the geometry of the Hadamard parametrics terms, then you could do better than a log lambda. And I see why that would necessarily, I don't see any way to exclude that possibility. It would be very interesting if it was sharp, but I would be shocked if it was sharp. I would expect the bound to be perhaps even as good as lambda to the n-1/2, I think, are the lower bounds that Dima and Yosef and John showed.
Right. Yeah. So I think it's as Blake said, there are basically no chances that this log lambda is a sharp thing. The problem is that getting even an epsilon polynomial improvement in, say, in the negatively coerced case is an outstanding problem. So nobody has achieved that.
Are there any numerical results to suggest like what the proper order should be?
Well, I know of numerical results for well, for the torus, right? So for the torus, you definitely have, it's like basically a Gauss circle problem. So there you know what the right exponent is. So in the negative curved case, good question.
And random wave conjecture predicts that for generic negatively curved metrics, right, eigenfunctions should sup norm should grow slower than any power of lambda.
Right. And
So
also, like in 2
that's very
dimensions,
strong.
right? So in 2 dimensions, the conjecture is that in the negatively curved case, generically I should have indeed lambda to the power epsilon for any epsilon, at least for the integrated counting function, for the true counting function. I'm not sure about numerics. No, I don't know.
Questions or comments? If not, let's thank Blake again.